That's loud. Um, okay, so good evening and welcome back. I hope your Tuesday and your week is going well. Today, what my focus is going to be is on probability, but in the new format schedule, I'm going to spend like the first 20, 25 minutes or so on technology, and then we'll jump into the material itself, and then have about an hour and a half to get you started on the assignment, sort of practical stuff. And so I have on the screen Canvas. And Canvas is a so-called learning management system. And I run the course using Canvas. And so some of you, thank you for the emails. You've emailed me your homework. But what I'd like to do is walk you through submitting your homework electronically online using Canvas. And so if you drive around the Canvas site, you'll see a bunch of sections. And one of the sections are the assignments. And so I've opened back up the personal branding assignment. And when you click on it, let me go to student view. As an instructor, I don't see the same things that you see because my view of Canvas looks different. And so if I switch to student view and you click on assignment one, personal branding, you'll see the following interface. And one of the things you can do, you'll see this button here in the upper right. It'll say start assignment. When you click on it, it'll ask you to either drag a file or choose a file. So then if you click on this, it brings up a selection tool that you can navigate around the computer and find that file, whether it's a Microsoft Word file or a PDF file, which is your assignment. If you've chosen to take a picture, you can upload the picture if you choose to. And so what ends up happening is when I get all of them, um, leave student view. Um, I get a list of all the assignments, and it allows me to keep all of those submissions in one place. So then I pull up that interface in my view, and I scroll through them, I grade them, I can comment on them and leave comments for you that way. It just works a little bit better for me to help manage the course efficiently by having things digital and to also, to be able to work on stuff regardless of where I am or what I'm doing. Okay. Any questions about Canvas? No? So if you have your computer up and you get to the Canvas site, you can certainly submit the document. If you've emailed it to me, I have received it. I do have to kind of sift through literally 100 emails a day to try to find emails. So please, if you could help me out, that'd be appreciated. Take the time to upload your assignment in Canvas if you have it in a digital form. Okay. Yes, Clarence. Oh, good. Great. Great. Thank you. Into the document. And one of the things I won't show it to you here, because I consider it your private information. There's something on Canvas called Gradebook, and I program in how much each thing for the class is worth, and it automatically calculates what your grade is, so you can always see how you're doing, right? That's one of the things, one of the reasons why I use Canvas, rather than have to write stuff down in a book or keep it in a spreadsheet. Okay, so then the next thing is Slack. And thank you, for all of you, for joining the Slack channel. And in Slack, it's a messaging system. You can access it through the browser or through an app on a cell phone or an application on the computer. And you'll notice here on the left-hand side, I can select one of these names, fundamentals. I should have said, I spelled it wrong. Fundamentals of AI. That's a so-called Slack channel. And everyone who's joined to this Slack system, when you send a message in this fundamentals of AI channel or group, everyone in the class will see it. So if you have a question about the class, maybe could you provide some clarification on this question on the homework? I'll see it and I'll answer it, and then everyone can benefit from that interaction. Yes, to everyone. Ah, great. Um, what's your name? I'm sorry again. Nelson? Nelson, was this your reply? Yes. So you've replied to my message. Maybe I'll go over some Slack procedures, right? So whenever you want to send something, you've responded to my message. So you can certainly type a test message, right? And it appears. When you put your mouse over it, you'll notice this pop-up happens. And if you click that little bubble, it'll reply in what's called a thread. And so it'll associate all of those messages anchored in that first level message. So what you've done, Nelson, is you've responded to my message. If you wanted to identify or quote unquote tag an individual, I could say at symbol, at, and it pops up a list of all the names in the channel. If I select your name and say, this is a sample tag, now you get a notification that Gary Holness has sent a message specifically for you, but everyone sees that. Moreover, here on the left-hand side, if I click on your name and type a message, this is a one-to-one message, you will see that, but not everyone in the class will see it. So in Slack, you can send messages to the entire channel, everyone in the class, or you can send messages to just an individual. And it depends on what you select. And yes, Nelson. I'm sorry. Ah, you have to put the selection over this message, right? Yeah, and then it should bring up reply in thread. And that's how you associate them together. But you don't have to reply in thread. You could reply directly as a message. You could tag people, put their name, or you could do good evening, or you could reply as a thread. There are different ways of interacting. Okay. All right. Awesome. All right. Yes. Okay. Okay. Oh, yes. Yes. Zoom recording. All right. So, any questions about Slack and Canvas? Let me put my glasses down so I can actually see. Any questions? No? No questions? Yes. Where to find Slack? I've taken the liberty to add a link to the course Slack channel from the Canvas site. So if you log into Canvas and you scroll down to the section titled Communication, just click on the link and it'll prompt you to log in with the um, Clark email and whatever password you specified when you set up your Slack account. Okay. Now that Slack account lives on my Slack so-called workspace, right? If you go to a different Slack workspace, you're going to have to register there. And so Slack allows anybody to create basically a website, if you will, but it's not really a website. It's called a workspace, and that allows you to communicate. So you could, create a Slack uh, workspace for you and your friends or you and your family to just chat and stuff like that, right? It's pretty neat because if you, for example, let's say you were planning a vacation or a road trip to go someplace, then you could create a channel for road trip, and now all of that chatter is kept separate based on specific topics, which is what makes it kind of nice. I'm using the free version. The free version maintains a 90-day history, and after that, it cuts off the old stuff when you've exceeded the 90 days, which is good enough for a semester or half a semester. Of course, there are many opportunities people will accept money from you, right? The pay version has an infinite history, and it's, I think, $2, $2.50 per person that participates on it. So it can add up very fast. For most people, the free version is good enough. Okay. And so I'm not doing anything in creating this Slack workspace that any of you could absolutely go to slack.com, create a workspace, send out invites like how I did to all of you. They join and then you're up and running. Um, I do that with my brother and some other folks because it just works better than email. Email, you're getting all of these messages from God knows who, right? So, all right, any questions about Slack? And so I encourage you to use it if you have questions about stuff. And I really encourage you, if you could do me a favor, please, to submit your homework via Canvas. And that helps me to better manage the class because I see it all in the same place. It doesn't get polluted with 100 other emails, and it allows me to not have to search for things. It's just sort of presented to the front. Okay. Any questions? Everybody doing good? Yes. Ah, I see. I see. Okay. All right. I'm gonna have to search for that, and I apologize ahead of time. I literally do get over 100 emails a day, and so every Friday I spend hours just sifting through stuff. But I'll see it. I'll see it. Okay. And could you say your name? Oh, wait, don't tell me. Black. All right. All righty. Okay. Any other questions? No? All right. So let me stop the share, and I'm going to bring the slides to the front. And this is a lot of the same material that I've gone through in some of my other classes. So I hope it lands how I intended it. What I really wanted to do is show you a little bit extra topics in probability. And then we're going to have about an hour and a half on the tail end of today for you to start on the probability homework. And in the exercise, what I'd like to have you do is use Copilot to create visualizations to help you understand the questions. And so one of the things that things like Copilot, ChatGPT, Claude, and all these large language AI models are good at is helping you to learn things, right? Um, I was working on something in a server room that I don't have a background in, so I asked ChatGPT, tell me about why I would do this versus that, and it did a great job. And then I said, well, show me a picture of an RJ45 jack, right? And so showed me a picture. Okay, so it's really nice tool for creating a so-called curriculum, things that help you to decide what it is you need to read or learn in order to do something that you might not already know how to do at the moment, right? And so one of the goals with this exercise, it's not so much about probability, well, it is, but it's more so about using ChatGPT, and Copilot is ChatGPT underneath the covers, to walk through an exercise of creating visualizations. Right. Question? Oh, yes. Did you not? All right, there we go. I like to, you're welcome. I like to, anyone else? Okay, the country. Um, did you get one? Homework? Okay, there we go. All right. Oh, okay, all right, no worries. Um, I give these printouts as a backup. Any other questions? No? No questions? No? All right. So why don't we jump in? Administrative. So the reading has changed. We're going to have some reading from what just happened. Oh, oops, that's not good. Let that cut out. That's not supposed to happen. I hope we're not going to have technology issues. All right. Um, so the reading, I have some reading, and this is going to be from the book, the AI Prompt Engineering Bible. And so you're going to be reading the introduction as well as book one. This, you know, describes itself as being seven books in one, right? It's not really seven books, it's seven sections, but you sell more if you say seven books in one, right? Um, so we're going to start more formally next week with all of the actual prompt engineering stuff as it relates to getting out of these large language models what you intend to do. And then that's the reading. And so we talked about Slack, we talked about Canvas. So we're going to spend about 40, 45 minutes on random variables and joint probabilities, which is building on the stuff that we had last time to add a little bit more sophistication to lead up to what sort of things these AI models are doing underneath the covers. Now, of course, it would take like maybe 3 semesters to really get into the heart of it, but I just want to give you a sense of what it's doing to reinforce the idea that these things are not magic solutions, right? They make mistakes all the time. And when you see how they construct what they construct underneath to be able to answer your prompts when you input to them, it'll help you to understand that, yeah, this thing is very far from perfect. Okay. All right. So in usual fashion, I have my corny dad jokes, right? I can't really tell them to my daughter anymore, but so I try to tell them to my students. Um, so what happened to the cheese factory that exploded in France? If you share your thoughts, what do you think? What happened? Cheese factory in France exploded. Cheese Swiss, yes, that's a good one. Good one. Any other thoughts? What happened to the cheese factory? Just went boom, cheese factory. No? Cheese spread? Okay. Some good answers, yeah. Nothing left but debris. This is one of my favorite ones. All right. Thank you for chuckling. It makes me feel good. My daughter just kind of rolls her eyes and doesn't say anything. All right. Okay. So why don't we jump forward with the material at hand? So when we talk about probabilities, we talked about coin flips, we talked about die rolls, and it was important to list out all of the possible observations that could happen. And so, more formally, all of those possible observations are called the universe. Everything that exists is there. And so, for the die roll, we draw this diagram called a Venn diagram, and we label it with this omega, this fancy Greek symbol, which is our so-called sample space, or sometimes it's called the universe of consideration. It's everything that you could possibly observe. When we looked at, oh, I forgot my coin. When we looked at the coin flip, this universe only had 2 items. It had heads and it had tails. When we looked at the die roll, this universe, which is depicted there, it has the one, two, three, four, five, and six outcomes. If you think about something like Powerball lottery, that has a much bigger universe. It's all the possible combinations of numbers that you can select, which numbers roughly 350, 360 million different combinations. Now, of course, if I were to draw it on the board, I would have a lot of different combinations. But theoretically, it does exist. And what makes something like Powerball very hard to win is that this universe has a lot of individual objects. And I'm going to give those objects a name. I'm going to call them particles, right? And so in the case, hey, Mella, of this example for the die roll, I only have 6 particles in the universe. Thank you. Um, the one particle, two, three, four, five, and six. Does that make sense? Any questions? No questions? Okay. And so another interesting universe has to do with cards, right? And with a card, we have 52 different cards. And these cards are of, and I always mess this up, 13 suits. There's the spades, there's the diamonds, there's the clubs, and the what's the other one? Spades, diamonds, clubs, and hearts. Thank you, and hearts. And then each card has a value. There's two, three, four, five, six, seven, eight, nine, 10, jack, queen, king, and ace for a total of 52 cards. Now, when you play cards, there are some hands or selection of 5 cards for 5 card poker that have a higher value than others. And the reason why they have a higher value is because there's this notion that this particular set of five cards is much more difficult to obtain, right? So literally, you can calculate the probability associated with different hands. And people who are really good at poker, in their mind, they're sort of actively computing some representation, some notion of probability. It's just you don't want to do that in a casino, right? There's nothing bad about it per se, but they really frown upon it and they'll probably throw you out for doing that, right? But nonetheless, when we talk about an event, we said an event is an observation. We talked about flipping a coin. You saw the heads outcome or the tails outcome. Whenever you see an outcome, essentially what you're doing is taking all the particles in this universe of consideration, everything that you could possibly observe, and you're carving out from it some subset of it. For example, this event I'm labeling A. It doesn't matter what it is, but this event, it looks through everything you could possibly observe, and it says, I'm going to take this one thing, the one particle. Now, when you do that, we say carve out subset, this symbol here, that this thing we're calling A, in this case, it contains the one particle, only the one particle, only has one thing. It's drawn or carved out by selecting some set of particles from all the things that we could observe. Does that make sense? Any questions? And Sai can attest it's the same thing from, stochastic computing. All right. So nonetheless, now, when we want to talk about the probability, like we said with that Babyface song, everything comes from the 80s, right? R&B. I love 80s R&B. But nonetheless, when can I see you again? We want to know if we roll the die again and again and again and again, when can I see again this event that we're calling A? So what we're going to do is we're going to do what I call mechanize it. We're going to think about the procedure that you would perform in order to compute this idea of when can I see you again. Does that make sense? And so what we're going to do is count. This count is called cardinality, and we're going to compute or count the cardinality, the number of particles in this thing we call A, and we're going to divide that by the number of particles that we see in the whole universe. So if we do that, well, people have, if you, look stuff up or ask ChatGPT or what have you, many people have different ways of saying the same thing, right? I don't know the history behind why. So one of the ways they say it is they put these vertical bars around that name A, and that means the magnitude. How big is it? And you can think of how big is it as counting the number of particles that are carved out in this subset that we're calling A. Okay. So we say how big is A upon how big is the universe. Okay. Another way of people saying this is the number of favorable outcomes, N sub F, upon the total number of outcomes, N sub T. So if we do that, okay, the number of particles in A here, how many? It's just one thing, the one, right? The number of things in the whole universe, one, two, three, four, five, six, there are six of them. So if we calculate that, that's one upon six, which is roughly 16 and 2/3% as a probability. And probabilities are always percentages. So that means if we roll the die again and again, yes, I'm sorry, percentages, percentages. And that comes from, if you're curious, per centum from the Latin by the hundred. You always express it by the hundred. And the reason why you always express it by the hundred as a percentage, if you had, let's say you were uh, selling, I don't know, t-shirts or something like that, or you're selling some item, right? And you said on this day, um, my customers started as 50 people and it went up to 75 people. And then another person had a store and they said the customers went up from 100 people to 150 people. Well, if you're trying to compare them, did they increase in the same way? Without thinking about it, you'd say, gosh, well, one increased by 50, the other increased by 25, right? But no, you have to register it by the same amount, by the 100, because it's both 50%. So it's really important that when you express this, when can I see you again? You want to make sure you're making a fair comparison. And you do that by changing it to by the 100. Does that make sense? Any questions? That's really, really important because, you know, you can use summaries and descriptions to tell all sorts of lies, right? You can say, well, my customer count increased more than yours. No, it didn't. It's the same 50%, right? So it's really important to make these fair comparisons to register things by the 100, by the percentage. Yes, should be like apples and apples. And how you do that is changing it to be by the 100. Mm, okay, great question. Any other questions? No? All right. Okay. So here's our universe of consideration for the die roll. We have all the particles, the one, the two, the three, the four, the five, and the six. I'm going to define a new event. I'm going to carve that event that has three things in it, the two, the four, and the six. Okay. Out of the outcomes for the die roll. We can give this one a name. It's called the even numbers, right? Even anything that is computed by adding two to itself some number of times, okay? Multiples of two. So if we look at all the things in this event that we've carved out, and any event is by carving out or selecting some subset from a universe of consideration, well, the two, the four, and the six, yeah, that's a valid observation. So if we wanted to know what's the probability if I roll the die and I get an even numbered outcome, now you can mechanize that. You say, okay, when can I see you again? How many particles in this event we're calling even numbers? How many particles in the universe? We take the size, that's 3 upon 6, that's 50%. And so if I were to ask you, which is more likely, which is going to happen more, or which would you rather wager on, gambling on getting a 1, rolling the die, or gambling on getting an even, aha, now you can make that comparison. Even is 50%, a 1 is just 16 and 2/3 percent. That makes sense? And so this system of measures, any system of measures, we call a calculus. It's a way of describing things so that you can compare them and you can contrast them and you can ask questions, how similar do these things happen or how different do these things happen? It's really, really important to be able to do that. And probability is the tool that we use to do that. And then you can write computer programs that do this for you, and now you can input images and things like that and say, are these images of the same type of thing? Right? Absolutely amazing. But it's not magic, right? It's just some math, a description, and a way of describing steps in a process to make these sort of comparisons. But you have to represent it somehow before you can make comparisons. Does that make sense? Any questions? No? Now, you could spend a lifetime just doing probability. And I hope some of you do, right? Hope all of you do. Um, there's a lot of opportunity in understanding probability. I promise you that, right? Because at the end of the day, there are lots and lots of systems, scenarios, organizations where they deal with things that aren't the same each time, like how the die roll is never the same each time. But at the end of the day, they still need to make decisions, even though this uncertainty happens, right? And there are many things like that. Example, how many customers per shift are coming into the store over one day, 1 week, 1 month, the seasons of the year? Why would you care about that? Well, if you know how many customers are coming in, what's the probability of getting this many customers? Now you can make decisions based on what actually happens. Decisions like, if you're a coffee shop, how many bagels do I buy? How many coffee beans do I buy? How much staff do I hire for this particular period of the day or this time of the year, right? So a lot of opportunity in understanding probability. Okay. Mhm. Yes, the algorithm is the taking of an idea. It could be the idea in math or an idea in science, and you're describing a recipe, right? Um, it's a series of steps that you perform step after step after step in order to accomplish some goal, right? And so in the case of this, you say, okay, I have this event. I count the number of things in the event. I count the number of things in the universe. I make that division. The result I express as a percentage, and that's my probability. And so the algorithm part is taking the idea and laying it out as a step one, step two, step three, step four, etc. And in the study called algorithms, what we're concerned about is how many resources that series of steps, that recipe takes. And if the number of resources it takes is more than the computer or the system that you have to execute it, then you need to change how you do things. And that whole purpose of algorithms, that's the study of laying out specifications. But this concept is just the mathematics of probability. Yes. Well, the database large language model, yes. Hmm. Hmm. You have the algorithm running, and that algorithm is usually written in some computer language, and it runs on a computer. And as that computer runs, because it's electronic, it consumes power. And so if you have something like ChatGPT, which runs on hundreds of thousands of computers in a data center, each computer is going to take about 1,200 watts of power. And so if you take hundreds of thousands of computers, that's a lot of power. You ever like you run your air conditioner in the summer and your electric bill goes way up because you're consuming a lot of power, right? Hmm. Oh yeah. Hmm. Yes. Hmm. 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 Excellent. Yes. Yes. The large language model. Yeah, absolutely. And if you find that your algorithm, in order to get it to run, needs is too big for one computer, you have to quote unquote parallelize it somehow. And so you get a lot of computers, and these computers get pieces of this algorithm. But that's not a magic thing either, because the more pieces you chop it up into, now they have to exchange messages with one another to coordinate. Okay, I finished my part. Are you done with your part? What did you get for your part? Let me put that with my part. And so if you chop things up, now you introduce additional time on a computer just for their coordination, right? And so you're absolutely right. You have a lot of CPUs, you have a lot of GPUs, they're in a data center, they're connected together through a network, and they have to exchange messages to coordinate with one another about the pieces of the large problem that couldn't fit in a single machine. Hmm. The AI, absolutely. I have a slide, a couple slides on the back end, but I wanted to take the opportunity to show you some of the concepts before I show you the application of those concepts. Absolutely. Okay. Any other questions? No? This is much better than the other class I teach. They just sit there and I don't even know what's going on. So thank you. I love this. I teach, it sounds weird when I say it, 1.5. And then I have some other projects with students that takes time. And I'm also chair of the department. That takes time, a lot of time. Uh, and then I advise students. And so for the computer science department, yeah. So you deal with all the problems. You deal with some successes. People ask for a lot of things. You marshal resources, you try to solve other issues, all of the above. You schedule who's going to teach what, when, and where, and all that stuff. It's the best job on campus, and at the same time, the worst job on campus. So, but anyways, um, so yeah, uh, where was I? I don't know if I answered your question or it was just a statement, but nonetheless, you can think of more complex things. We talked about a die roll. What happens if you had the roll of set of two die? So now this is more complex. And by complexity, I mean the number of outcomes is bigger. If you have each die, the first roll and the second roll, there are six choices for the first roll. You multiply that by the six choices for the second roll. That's a total of 36 choices. It just got bigger by a factor of six. And each time you add a die roll, it gets bigger by a factor of six. So it gets very big, very, very fast. If we were to draw this visualization of the roll of two die, well, you'd have the first die is one and then one, okay? One and then two, one and then six. Then you'd have two, then one, two, then two, two, then three. And so if you listed this out, this is a total of 36 different things you can observe, and you draw that as these 36 quote unquote particles that are in the universe. So one of the questions on the assignment talks about what is the probability that you roll the first die and you roll the second die and the sum of the two is greater than seven. You can absolutely calculate that. Register it as a set of particles, and I'm not going to tell you the answer, but I'll leave that to you. So this idea of mechanizing complex things is really, really important, but we're going to extend that idea, and I'll show you in a couple slides and show you how that's used in these large language models. But I can't show you the actual large language model. It's too big, right? I can show you how it does something in a small example. Okay. All right. And plus, ChatGPT won't tell me exactly everything they're doing, right? That's their secret competitive advantage as a business. You'd have to get a job at OpenAI to get that information. Yes, there are algorithms specifically that look at how frequently probabilities some words follow other words. And I have a visualization of that. And if you do that for enough words, for enough documents, you get really, really good at it. Yes. And it does it not just for words, it does it for images. It does it for sounds. It does it for an unfathomable amount of data. Lots and lots of data. So much data. It's not just one data center. It's several data centers dotted throughout the country and the world, right? Mhm. Because it's listened, or I shouldn't say listened, it's inputted. See, I tend not to humanize inanimate things, right? It it ingests or inputs lots and lots of sequences of sounds and music. And so what it's doing is saying this sound follows that sound. That sound follows the other sound. And if you do that with enough sounds and enough music, now you can generate things, you can listen to things, or you can input new things and you can generate things. But all it's doing is just saying, okay, this sound tends to want to follow that sound a lot because music isn't arbitrary. You don't have one random sound following another random sound. It sounds weird, right? You always have certain types of sounds preceding and following other types of sound. And that's what makes it music because it's pleasing, right? Um, so yes, it's music, it's images, it's text, it's all sorts of things. Yes. And how you encode is this idea of what comes next. And you're looking at how things come next for lots and lots of data. And you see different ways of how things come next in a really big way, in a lot of data. Mhm. It is software. It's programs that are running and they're running constantly. And if you do that for lots and lots of data, then you get really good. Anything anyone can ask you, not even just in English and other languages, including slang, right? I tried slang with ChatGPT, and yeah, it does it. Well, not completely, but it does it, right? It tries to. It tries to. but it's okay. But I wouldn't, I wouldn't recommend somebody use it for that and then try to speak what it's telling it to say because you might find yourself in a situation. So, yes, well, it's only the data that it sees. It only knows stuff from the data that it sees. Hmm. 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 Yes, because slang changes. It's very much linked to what's going on at the time, right? And it changes, and it's also very local. You know, the street that I grew up on, we said different things from cross town, right? It's very, very local because the meaning of what happens changes from neighborhood to neighborhood. It changes. Yes, yes. And then, once it makes it into popular culture, like on TV shows, it's very different, like live in place, than it is once it makes it to popular culture. Oh, yes. Hmm. Yeah. And the sort of insidious part about it is that, let's say you're a very creative storyteller and you bust your tail writing stories and you just happen to have it online. Well, ChatGPT's computers, they go out and they look for data. They find your story. All of a sudden, the patterns in your story are now inside ChatGPT. So somebody who hasn't been working as hard and having your imagination and your life experience just says, I want you to write me a story. All of a sudden, some of the stuff it generates is some of the stuff that you worked on. And that ownership um, is an interesting problem, right? Hmm. Hmm. Mm. Nope. Yes. Hmm. As helpful as it is, it's also using your data to update its probabilities. It says, oh, great. Here's another source of words that follow one another. I'm going to use this. Ooh, wow. He has a very interesting way of words that follow one another that I don't really have much examples of. I'm going to use this, right? It's exactly. It's, any other questions? No? Do you remember the Hulk from Lou Ferrigno, the old school one? Yeah, yeah, yeah. Now, my brother and I have had this thing. This goes way back. Dr. David Banner, every town he was at, it wouldn't be more than first day or two, he's getting into a fight, turns into Hulk. Maybe Dr. David Banner has a problem and not the people around him. Anyways, but that was just, we call it the Incredible Hulk syndrome. Um, this, we still, anyways, when you're little, anyways. Um, so, all right. So this, when can I see you again? Whatever you're doing, that event of the sum of the two die is greater than 7, you take the size of that set of particles, divide by 36, and there's your probability. Okay. Any questions? No? All right. So this idea of events and counting is very simple, and we need a little bit more sophistication in order to connect this to the real world. Now, in the real world, when you measure things, you measure sensors from sensors. You measure things like temperature, like take a picture. That's a sensor. And so, this idea of an event being carved out of your universe of consideration, it's not enough. And for example, let's say you have a heart monitor and you're measuring the heart rate. One of the representations of cardiovascular health is this idea of recovery rate. If you do a bunch of stuff, you're running on a treadmill, full speed, whatever, and then you stop, how quickly does your heart rate go from whatever it is at your max performance back to rest? The faster that happens, that's a sign of good recovery, which is an indicator of good heart health, right? And so with that, you don't just measure 10 beats per minute, not 10, 100 beats per minute, 120 beats per minute, 180 beats per minute. Um, you want to measure the change in your heart rate. And so that means that you don't just look at subsets of particles, you want to look at functions over those events. And those functions have a name, they're called random variables. And a random variable you can think of is just a function. And I'll give you an example of what I mean by that to motivate this idea of how data behaves as a distribution. So let's imagine I have three coins, and it's the same problem if I flip one coin three times. But for the sake of argument, let's say I have three coins, and my measurement or random variable, I'll call it big X, it's going to measure the number of heads. So if I have an event that's tails, heads, heads, that's the event, right? That's one of the combinations of things that can be observed. But the function is going to go over tails, heads, heads, and it's going to count or measure something about this event. And so I really want to drive home there's the raw event, the thing you observe, but then there's stuff you measure from that event. Does that distinction make sense? Okay. So let's define a random variable x, a measurement, and it's going to measure if I flip three coins, how many of them come up heads. Okay. Now, we know a coin is 50-50 probability. And what we do with the first coin doesn't impact the second coin and doesn't impact the third coin, right? They're so-called independent observations. So whenever you have that case, if you want the probability of those three coins, you're going to multiply the probability for the first coin flip with the second with the third. Okay. So let's look at what values we can get. The number of heads for three flips can be zero, right? That's tails, tails, tails. The number of heads from three flips can be one. You can have a heads in the first flip, a heads in the second flip, a heads in the third flip. The number of heads can be two of them. You can have heads, heads, tails, heads, tails, heads, tails, heads, heads. The number of heads in three flips can be all three of them. You could be really lucky, right? And get heads, heads, heads. So in each case, the probability of each one of those heads or tails is one half, and we're going to multiply. So if we do that, okay, tails, 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 that's one half. The first flip, one half, one half, that's one eighth. Okay. If we do that for the next one heads, we have to add up all those different cases. So that's one eighth plus one eighth plus one eighth, that's three eighths. Likewise here for two heads, that's one eighth plus one eighth plus one eighth, that's three eighths. And then lastly, heads, 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 that's also one eighth. So why do we care about this? I'm like, oh, why you tell me this? Okay. This describes how this particular system behaves. So we have a different probability, one eighth, three eighths, one eighth, for each one of these measurements that we can get over this raw event. Does that make sense? All right. And so if we want to summarize how the three coin flip works, let's put it in a table. And on the right-hand column, we're going to have the probability that the measurement happens. And in the left-hand column, we're going to have the value that it takes on. We can have zero heads for three flips, one heads, two heads, or three heads. So one of the things that you'll notice here is if we add up all of these probabilities, it adds up to one, right? That's important for probability because if you look at anything that can happen, it has to add up to one. And this table summarizes everything that happens about the values 0, 1, 2, and 3 that can occur with this particular measurement or this random variable. Does that make sense? So we're listing out all the possible values and the probability that each one of these values for the measurement will happen, right? When can I see you again? Okay. So this catalog of probabilities for all the values is called a distribution. And a probability distribution is just an accounting of everything that can happen and the associated probability, that percentage of how often it's going to happen if I flip three coins again, Flip them again, flip them again, flip them again. Question. Ah, because it's a measurement. That's a great question. If I flip this coin and the measurement is how many heads I get in three flips, if I say tails, 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 how many heads are there? There are zero heads. Likewise, if I flip it and I got heads, 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 and I should have made two more of these, heads, 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 how many heads do I have? I have three. And so with this particular measurement, it's going to take on values because it's going to measure how many heads do I see when I'm done with that experiment of flipping three coins. Did I answer your question? Every measurement is different. Any other questions? I'm sorry? Ah, it doesn't have to be. It depends on the measurement. So if I measurement was, um, you know, I could say the number of heads divided by two, right? Or I could say the number of heads is greater than the number of tails. And so it all depends on, and that's a great question. It depends on what your measurement is. And different measurements are going to take on different values depending on what that measurement does. Yes. So if this measurement was how many tails, then we'd have these would be reversed. That makes sense? Okay. So it all depends on the measurement. That's why in this expression, I say let X be a random variable measuring the number of heads, right? And this is a very specific procedure, this measurement. Does that make sense? Great. Okay. So if, for example, this case is pretty small, right? We only have four different values that this measurement can return. That's pretty easy. What if we had 10,000? A table with 10,000 entries? Gosh, that's kind of hard to manage. So instead of using a table, it's visualized, these distributions. So along this horizontal axis, we're going to have some tick marks, and each one represents a different value that this measurement can take on. Along this vertical axis, each tick mark represents a probability, 1/8, 2/8, 3/8, 4/8, etc. So we said for this table, for zero heads, it was 1/8. For one heads, it was 3/8. For two heads, it was 3/8. For three heads, it was 1/8. So now we can connect them together. And one of the things that you see is as the number of heads increases, the probability gets bigger, then it stays flat. And then if it gets really big, it starts to decrease. Now, this shape here is more important than the individual values in the table. So a lot of times you just remove all the other stuff and just look at the shape. And if I were to ask you, gamble gamble on three flips of the coin, how many heads do you think are going to come up? Right? And you say, well, I think this many heads. And then we wager, and then I flip it three times and we see what happens. If you knew this is how it behaved, well, you know that one heads and two heads happens three times as much as zero heads and three heads. They a little bit because it wiggles so much that you have to do other stuff. Yes. hmm hmm They they try to describe this wiggly graph for the stocks with straight lines that kind of try to describe it because it wiggles too much to do it exactly. But yeah, absolutely, it's a similar thing. hmm Oh, nice. Wow. Yeah. Yeah. Yes. hmm hmm Yes. hmm Yes. So you're looking at V structures, a teacup, an inverted teacup. You look, yes. hmm hmm Yes. Yes. hmm hmm And they see that shape again and again and again, that means there's a high probability it's going to happen again. And that's a measurement of a raw event. The raw event is the stock is this, the stock is this, the stock is this every 5 seconds. The measurement is that line that, um, yes, because we want to know all the values, how many heads can take for three flips. And it includes zero because zero can happen. It can absolutely happen. So you have to account for every single particle, if you will, every observation that's possible to see, your universal consideration. So for this measurement, that includes zero. It has to include zero because you can flip 3 times and get zero heads. And so it's about looking at the accounting that says, have I considered everything that I could observe if I flip the coin 3 times? And you have to do that because if you don't have the zero there, you haven't fully described what could happen. And if you're going to wager on it, it's not going to work out very well because it's going to be unexpected when you get a zero. Okay. All right. Any other questions? Yes. Oh, it's a huge business. hmm Oh, yeah. hmm hmm And there's a movie about that called Moneyball, right? And it was, yes. All right, take care. And and it makes sense, right? If you're going to recruit a player and you're going to pay this person a salary, you do it on the probabilities of if it's basketball, a field goal percentage, or if it's football, pass completion, or things like that, right? Because they use all this data to make informed decisions. Absolutely. And then even not even just the pro teams and the amateur teams, um, also for like FanDuel and all those DraftKings and all of those fantasy things, it's there's a lot of monetization. Again, it's another way understanding and mechanizing probabilities. There's a lot of opportunities. hmm 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 Oh yeah. Oh yeah. And they update that based on what's happening, right? Someone gets injured, they update the probabilities. Someone is having an off week, they update the probabilities. Absolutely. All right. So this shape describes how this data behaves, the quote unquote aboutness of this system X. Okay. All right. And so I'm not going to belabor this one. It had to do with wagering. If you're going to wager on two different systems, the probabilities for a system we call with measurement X and measurement Y on the left and on the right, which one would you rather wager on? This one or that one? Why would you rather wager on Y? Let's see. Let's unpack that. hmm At that certain, let me. hmm 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 Okay. Let me pose a scenario to you. Y can be 0, 1, 2, or 3. You want to wager on whether Y is going to be 0, 1, 2, or 3. X is going to be 0, 1, 2, or 3. You want to wager on that. So if you pick a Y, they all happen with the same probability. So if you pick one and you guessed wrong, how many ways can you get it wrong? You can get it wrong this many ways because they're all the same probability. With this one, this probability has something called structure. Some of the choices are going to happen 3 times as much as other of the choices. So if you're watching a system unfold, someone's flipping a coin 3 times, flipping a coin 3 times. The moment you recognize that there's some structure, some things are preferred more than others, if you guess this one, that's 3/8, you're only going to get it wrong 5/8. If with this one, you guess this one and got it wrong, 2/8, it's 6/8. You're going to get it wrong if you pick the wrong one. Question, yeah. No, it's not on purpose. Um, a lot of probability and statistics was developed because of gambling. Don't believe me. Look it up. Ask ChatGPT. There are techniques called Monte Carlo methods, right? A lot of it had to do with gambling. Oh, the card counting team? Yeah, yes. Hmm. Hmm. Yes. Because they want to make sure it's fair, but I would argue it's probability. It's not cheating. You're not doing anything wrong, right? Doing something wrong is putting weights in a die, right? But just looking and thinking is not wrong per se. But you're right. They really don't like that, um, because it advantages you, and they would rather you just rely on luck or probability. Hey, you never know. You never know. Okay, so what you look for is structure. Now, the reason why structure is important, think about in another application that's non-gambling. I don't want to present it as just all gambling, right? Um, a self-driving car. This self-driving car, it has a laser scanner and it can see how far things are away. And it has a camera, among other things, and it can take pictures of what goes whooshing by. Now, if you think of obstacles in the environment, that pedestrian walking across the street, that's going to be more like this. That fence that it detects, that's going to be more like this. What structure looks like in probabilities for autonomous cars and sensors is there are some things that you measure that stay the same. So if you measure it, it's going to have that value again and again and again and again and again. And what that means in a probability distribution is that the probability is going to be really high for some values, very low for all the other values. And so, how you represent landmarks in your environment from sensors is you look at the probability of the measurements, and this one seems to have a high peak over some values, really low. Aha, I can rely on that, right? And so, for identifying landmarks and sensors, this idea of structure and probabilities is really, really important. Okay. Any questions? Hmm. Absolutely. Yeah. Yeah. Yes. Yep. Yes. And so one of the questions with that, who gets the lawsuit? Is it the car manufacturer or is it the person who owns the car? Lots of questions. Hmm. Yes. Hmm. Hmm. Now, I don't have a Tesla, but I know one or two people who do. And for Tesla, they have the autopilot feature, they call it, self-driving. They say it'll drive itself, but you're really supposed to keep your hands at the wheel, right? So they try to kind of get out of it, their liability that way. You're absolutely right, because you put the person in a bad situation. But, lawyers do what lawyers do, right? Hmm. Hmm. Okay. You could use probability to clean up photographs that are old photographs. You can use probability to group things together. If you have customer records, you can group them together. Stores do that all the time, right? You look at what they're purchasing and you group them together, and then you give those groups names. These are the young families. These are the single young people based on just what they buy. And then at the kiosk, you ever go to like a store and when you're done and paying, they print out these coupons that are related to what you bought, recommendation systems. Or you click on a website like Amazon and it says, well, you just bought, I don't know, an Xbox. You might like this. That's probability clustering, right? So there's lots and lots of things, recommendation, um, grouping things together, restoring photographs, all sorts of things you can use probabilities to do. Okay. Yeah. Sure, sure. Hmm. Oh, you did? Okay. Neat. Neat. And the neat part is, I mean, it's mathematics and it takes a little bit to learn it and understand it, but math has been the same for hundreds of years. You learn it once and you're set for life. I promise you that. Yeah. Hmm. And it's really important to them. Really, really important to them. Hmm. As a control to, yes. Yes. A lot of companies will make decisions based on data. And if that data concerns uncertainty, then they're going to use probability. No, no, no worries. Yeah, yeah, I'm pretty sure. Hmm. Hmm. Yeah, yeah. But if you put humans into it and they, is that the swipe left, swipe right one? Then it's human judgment, right? But you could use probability to take your photo like I did, beard, suit, and all that stuff. So then there's sort of false advertising, right? But anyways, yeah, and the Harley. Or, but you know when you see people have those pictures where it's clear they were with somebody and they just cut it in half, you could clean those pictures up. So you could have, I'm not saying you should, uh, a dating site picture cleanup service using ChatGPT, and somebody's probably going to pay you to do that. But anyway, but yeah, yeah. All right. So in the real world, we've talked about measurements like the number of heads, right? And that's kind of nice and cute. Okay, fine. But in the real world, you have many ways to describe the same thing, right? So let me ask you, how do you describe this picture? First, what is that? And it's not a trick question. A bunch of apples. Okay. So how do you describe different colors? Color is one way. Is there anything else? That's a measurement, which is why we talk about random variables. Okay, the stem, and the stem is a different color and it has a certain curvature to it. Shape. Okay. And how you describe shape is if you're to get little lines, those lines are going to be at different angles, right? Okay. Anything else? Color? I'll give you this third one. Texture. If you scan from one direction to the other, you see the color change in a certain rhythm or pattern. Texture is the change in color over space as you move. So there's color, texture, and shape. Okay. Each one of these is a measurement. Now, if I were to show you pineapples, do those look different? How do they look different? Color, texture, and shape. Exactly. So we see different shapes. We see the different color. This is more brown and green and a little bit of gold or yellow. So this color, texture, and shape, those three measurements together, certain ones come together for pineapples, certain ones come together for apples. If I were to compute this and show you a distribution, you would see the structure in different places for different values of color, texture, and shape. And so this is just to say, when you describe probabilities, it's not just a single measurement, it's the co-occurrence of a set of measurements that means, or that defines rather, what it means to be a pineapple picture versus a picture of apples. That makes sense? And so that means we need more than one random variable. And this is called a random vector. It's a collection of random variables, different measurements, whose values occur at the same time. And these values occur at the same time with a certain probability. And it's that structure in these vector-based probabilities that define what it means to be an apple picture versus what it means to be a pineapple. And I can do this with all sorts of things. And you mentioned like, call logs, or we mentioned pictures of things. You're going to take many measurements. And in a real computer vision application, you can have thousands of measurements that collectively define what the content of an image is. And given that, if you go to like your photo library or something like that, you know how it'll recognize the faces and they'll group them together and stuff like that. It's doing exactly that. But you need a lot of measurements to describe content of images because images have a lot of stuff in them. Okay. Any questions? No? All right. And so to give you a concrete example, let's say I roll a die and I flip a coin. And this word fair means that no one outcome is preferred over the other. It's 50-50. It's 1/6, 1/6, 1/6, 1/6 for everything. And so here, I just wrote it. Probability of a die is one outcome, is 1/6. For heads or tails, it's 1/2. So together, I have 1/2 times 1/6 is 1/12. So if I said a particular value of the die and a particular value of the coin at the same time, this joint probability, I can put that in a table. And so in that case, these are the die outcomes along the rows. The columns, these are the coin outcomes. So this cell is I roll a die and flip a coin. The die comes out two, the coin comes out heads. That happens 1/12 of the time, whatever percentage that is. I can't do that anymore. I used to be able to, I don't know how to do that anymore. Maybe Sai does, but I can't just take a fraction and then automatically come up with the proportion. So it's like more than 1/10, less than 1/10. So it's like, I don't know, like 8% or so. Okay, I can't do that anymore. Anyways, that part of my brain died off a long time ago. All right, so does that make sense? All right. And so here, you can take this joint probability and say, I want to produce just the probability of the coin. Well, if you did that, you'd say, where's the coin heads? I'm going to add up the coin being heads for every value the die can take on. So if I sum going down, that's 1/12 plus 1/12 plus 1/12 plus 1/12 six times. 6/12, that's 1/2. So I can get back what I know is the coin's behavior from this set. Does that make sense? All right. So I think this is a good stopping point, but let me just go forward to the who cares, right? Because I really want to end with that before we break. So we talked about different measurements, different descriptors, and the collection of measurement values, those probabilities uniquely define content or systems. So what can you do with probability to address your question? Um, this is an image, and you can do image restoration with probabilities. You present a system, descriptions of images, many different measurements. Let's say you had 1,000 measurements of things like skin tone, about shadowing, about hairline, about clothing. And you take those thousands of measurements and you compute them over tens, hundreds of millions of different pictures. Okay. Now you take a picture, scan of a picture that's really messed up. And then you say, okay, if this color is there, what's going to be next to it? Well, this probability says it's most likely going to be that color. And then you write that in. You do that for things like shape. You have the line between the cap and the head, right? That's an edge. What color is that going to look like? What orientation is that line going to be? And you can literally fill in these things from just building those joint probabilities, those probabilistic vectors over a lot of data. And this is tens to hundreds of millions of data to do this. So you can do image restoration with that. Mhm. This wasn't ChatGPT. Well, ChatGPT, I haven't tried it. I'm assuming it can do that, but they've been doing this from um like the mid 2000s. That's old technology. Certainly, I'm pretty sure a large language model can do it. It's just new technology doing an old thing. Um, mm, yeah. Looking at the DNA sequence, that's outside of my that's outside of my expertise, but you can use probability to do that. That's why, people who do like 23andMe and all those things, that's why you got to read that thing that they make you click, because what they're saying is you're agreeing to allow us to share your information with third-party partners, right? Those third-party partners could be the federal government, it could be other companies, could be insurance companies. Why would insurance companies want DNA information? Well, your DNA says you're more likely to get Parkinson's, so we're not going to cover you or we're going to charge you more. You don't have Parkinson's, but it's in your DNA, right? So you want to be careful about your data. So to answer your question, yes, they do use it for those purposes for DNA. I'm not familiar with that area. Absolutely. Oh, absolutely. Absolutely. I'm wondering, when you're in like Lowe's hardware store and they have that camera staring at you all the time, what are they doing with all that video data? I, you know, when I was little, uh, you know, yeah. Yeah. Hmm. Absolutely. Now, what if you just happen to look like someone who was in the store before, right? But if you think about all this data, the typical hardware store in an area like this, you're going to get different ethnicities, different ages, different heights, different body mass, different everything, gender, everything, clothing style, everything. That's a nice data set. Now, if I wanted to do detection of people, I would go to Lowe's and be like, I'll pay you some money to share that with me. And what are they going to say? Well, we're not just selling tools, we can sell data and make some money. And the data is just a few clicks on a computer, right? So the issue I have with it um, is that you don't know what they're doing with your data, right? You just don't know what they're doing with those faces and stuff. So, anyways, that's I'll get off my soapbox. But yes, Clarence, absolutely, absolutely. Absolutely. And you are entitled to privacy. Just because you assert your right to privacy, it doesn't mean something nefarious is going on. It means you're assuming and claiming your right to privacy. So there are browsers like DuckDuckGo and all sorts of stuff that are more private than otherwise. But absolutely, browser history, the cache that it stores on the computer, even the Google search. There's many cases where something goes down and um, the authorities, FBI, and police departments subpoena the search history, right? And they give it up to them upon subpoena. Hmm. 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 Yeah. And then also um, judicial systems compute risk scores based on there's police information systems. And if you think about what happens in an urban area, more densely populated, there's more crime, right? And so the demographic in urban areas is different from suburban areas. And so if you have more crime in the dense place and the demographic is different, that means someone who matches that demographic is going to get a higher risk score, which impacts sentencing, right? Through the same crime gets different sentencing. Why is that? Is because of that risk score. And so that's something that is widely recognized or beginning to be recognized by folks who deal with data and trying to, on the legislative side, fix some of that. But the court systems are like 20 years behind everything else. It's just really needs some updating. But anyways, so probabilities can be used for great things, can be used for not so great things, and one of them is filling in and restoring imagery. Okay. Any questions? No. And so this is what I wanted to end with. I should have started with it, but we needed all of that to get to this point. Suppose we have a document, and that document has a bunch of words in it, and language is not random. It's not just some arbitrary word somewhere on the page. The dog ran to the house, the dog jumped over the fence, the cat sat on the chair, blah, 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 right? So now let me build a big probability. And what this probability represents, and I have the same words along the columns and along the rows. And what the rows represent, this is the previous word, and the columns, this is the next word. So if I say dog ran, hair dog ran, I count one every time I see that in my document. So if I give it this document, some examples, I have dog ran, I have dog jumped, increment that. I'm counting. So those occurrences, one follows another, that happen more are going to have higher counts. And I can turn this into a probability. So now using this, you can say that it's more probability, more likely that if I say dog, it's going to be followed by a certain thing. Now, does that make sense? I showed you one document. What if I had 20 trillion documents? That's a million millions times 20. That's a lot of documents. And if I give you enough documents, and instead of just these 6 or 7 words, what if I had a couple 100,000 words? That's a really big table with 20 trillion documents. I'm going to do pretty well representing how words follow one another. So then you put this in ChatGPT, which is all it's really doing, and you don't just do one word follows another. You say one word 2 steps away from another. And then you do one word 3 steps away from another. So when you do this follows relationship, you're not just doing one step, you're doing 2 steps, 3 steps, 4 steps, 5 steps, 6 steps, as far as you can go. So now what you're doing is you're building this representation of how language is structured, because language is not random. It's stochastic. It's guided by probabilities. So when you go in and you tell ChatGPT, complete my sentence, the cat sat on the, and you say, oh my gosh, this is cool. It knows how to write. It's just representing somewhere in this enormous probability what should more likely follow something that you've typed. And it does this for words, it does it for images, it does it for sounds, it does it for all kinds of data. It's just easier to show you with words. Okay? And absolutely, the auto completion. And you see that with text messaging, you see that with emails, but also if you said, I'd like you to write me a story. So when it goes to that part of ChatGPT that has stories, it's a story about a young man who lives in, I don't know, make up a fictitious world, right? And then it goes to another part where it has things about that world. And it's going to be a sci-fi. So it goes to another part of the probability. And as you interact with it, giving it more sequences of words, it's narrowing down smaller and smaller and smaller and smaller into this huge, enormous probability table. And so the set of words that it considers, that's called the vocabulary. And so vocabularies can be as much as 500,000 to a million different words. And then it builds these tables from like 20 trillion documents, and there's another one for images, another one for sounds. These big probability tables are spread across hundreds of thousands of computers and data centers, and it's always going out trying to find new data. So if you are a unique storyteller and you have your stuff on the internet, it says, I've never seen words follow one another this way. Let me go grab that, and I'm going to include that because that means it's now filling in part of this table that was empty. right? That's more data. Same thing for music and for images. I've never seen brown follow yellow in this way. Oh, that's because it's a mango that doesn't usually exist in this part of the world. Yes. Hmm. 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 Yes. Yes. Hmm. 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 Because somewhere inside this probability table, where follows relationships, one step, two steps, three steps, 10 steps, 100 steps, that matched what you were talking about, and it just spat it out. So then you correct it, and then it says, oh, let me take a little bit of this other part of this big probability table. And so it's all about probabilities associated with follows relationships at different number of steps away. And that's for words, it's for images, it's for music. And if you think about it, speech, words, it's not random, right? Music, it's not random. When you have random for music, that's just like that sound that you hear sometimes and stuff. When you have random for images, that's just, these test patterns like fuzz on the TV from back in the day, right? But like you saw with the pineapple and the apples pictures, it's a particular occurrence. It's structure. And because of structure, if you do these follows relationships with enough data, enough steps away, you get pretty good at being able to answer things that people ask you, right? So that's all it's doing. It's just mechanization of this amazing stuff that runs in data centers. Okay. So that just says and that's all I had to say, but that just says trust but verify, right? Don't assume it knows what you're talking about. It's taking its big probability table and it's honing in on a particular location based on what you tell it. And so what you find with prompt engineering, when you give it something, you start with high level and then you narrow it down a little more and then narrow it down anymore. And you can almost imagine it's selecting when you said, um, let me just do that. When you said, tell me a story, maybe story, and I'm exaggerating this, is this part. And then you say about a fantasy world, then maybe it's this part. And our hero is a teenager in high school. Okay, then maybe it's that part. And then this person got their first car. All right, so maybe it's that part and it's linked together with something over here. So it links them together, right? So the more detail you give it, you're helping the model identify which parts of this big relationship table, whether it's images, text, or what have you, it should focus on. And then it's just looking at it and just playing things for you based on the values that occur more frequently. And then to make it seem a little human, it'll kind of wiggle it a little bit. It'll change it a little bit, not always select the best thing, but something that's not quite the best thing to give it that sense of imperfection, which makes it look quote unquote human, right? How do they do that? Ah, there's this classic thing in machine learning called exploration versus exploitation. When you see things and you say, this is my top choice, this is my second choice, this is my third choice, you might take the top five things and then you say randomly pick versus saying, let me just take my top choice. So you can absolutely do that. And if you change the size of the top group, if it's bigger, that random choice is going to be more off than just if you're doing your top three choices. And so that's all it is. You're just allowing some randomness among this idea of a top choice. Because in things like, yes, like in music, right? If you have like a music recommendation service, uh, if you always take the top choice, you're always going to get music that you like, that you primarily listen to. But if you take stuff that is similar but not the same, and you make a random choice, you might discover something you wouldn't have listened to. Oh, well, I kind of like that. That's not bad. I kind of like that vibe, right? And so sometimes randomization or not making the top choice is beneficial because you might discover something you wouldn't have considered. So you don't always want to select top choice. You want to sometimes purposefully make a choice that's not the top choice because you might discover something that is useful or beneficial to you. Okay? All right. So I hope I've whirlwind tour. I've dispelled some of the mystery behind what these things do. They are amazing in the scale that they're using, but they're really just taking an unimaginable amount of information, both text and video and imagery and music, finding all these relationships and then just presenting it to you based on what you say. That's all it's doing. That's it. I won't say that's all, right? It's pretty amazing, right? Um, but it's just a lot of brute force, to be honest with you. And it's doing it in an interesting way. But that's all it's doing. So don't trust what it says. You want to make sure that you understand what it's saying and you're being very careful in how you shape what it's doing. But it is also fun too, right? And it's a great tool, like the assignment for helping you produce visualizations for ideas that you might have. So if I were, for example, in my research, people publish their research. Now I take the papers, I put them in Chat GPT and say, summarize it for me. Okay. Produces a summary. Go, okay. All right. Can you get me what that's based on? Oh, you talked about Riemannian surfaces. What's a Riemannian surface? Could you remind me about that? Oh, and it just uh, I treat it like an assistant to help me slice through data and then producing visualizations and figures. For my classes, I use figures that it's generated. I have the picture in my mind and I describe the picture in my mind. It usually gets it wrong in the beginning. And then I kind of negotiate and I take some of it and I customize it and stuff like that. So you can use it as an assistant to help you visualize, to help you learn all sorts of things. It's a beautiful tool. And it's just based on the sheer unimaginable volume of stuff that it's finding relationships in. This is a toy, right, that I showed you, but this is the real thing, right? It's just a massive scale with different types of data. Does that make sense? All right. So I'm sorry I went over. I just wanted to finish that aspect to address some of the questions about why probability, how's it used in this thing, right? So we'll get a break and spend the rest of the time working on the homework for probability using Copilot to help you with visualizations. Now, some people start by just copying the whole assignment, put it in Copilot and see what happens. Some people prompt it, right? And I have some example prompts on the assignment. It's up to you, right? Okay. All right. Thank you. Sorry to go over like that for the half. So I'm just going to stop there. And as usual, I'll post the recording. I wish my other class was this interactive. You don't know. You just don't know, man. This is awesome.